Good morning, everyone. Welcome to the paper presentation session 6 of ICMICDS 2022. Participants who are doing presentation, please note that you are having only 10 minutes for presentation and 5 minutes for question and answer session. So the first paper presentation is doing by Dr. Ramkumar PB, presentation number CP38. Sir, are you?
Thank you. Myself, Ram Kumar, Professor, Department of Mathematics, presenting paper on applications of topological data analysis with morphology operators on hypergraph. These are the contents of my presentation. So hypergraphs are mathematical models which are used to represent mathematical problems in engineering and application. Topological structures are mathematical models which are obtained by identifying a topology on a specified structure. V.A. Kowalewski introduced finite topology, which can be applied to image analysis. Generally, hypergraphs represent relational structures. So we can consider the underlying topological spaces corresponding to hypergraph or corresponding to a simplicial complex. Mathematical morphology is an important tool that can be used to process images, data, etc. based on a structuring element which represent information contained in an object or an image. Jean Sir and George Mathron introduced this for the study of mineral characteristics, and later Heinzmann introduced graph morphology in image analysis. Isabella Bosch extended this to hypergraph morphology. Bino Sebastian defined hypergraph morphological operators in lattice framework. The falsification of this is also possible. So here, if you consider a hypergraph, this is a hypergraph corresponding to a crime data. Using morphological operators, we can construct topological spaces. The important morphological operators are dilation and erosion. So here, edge dilation is denoted by delta EXN, which retrieve all edges from H which contains at least one node in X. Edge erosion, epsilon EXN, retrieve all edges from H which contain the vertices or edges in X. So here, just as in the case of a graph, we can define a sub-hypergraph H of VE. And corresponding to that, if you consider this collection of sub-hypergraphs, that forms a topological space. So how can we define a topological space, underlying topological space using sub-hypergraphs? So for that, here we are using the definition using dilation and erosion on these sub-hypergraphs. So topology using dilation. So delta is a dilation operation on this collection of sub-hypergraph HF of H. And if you consider any vertex VIB vertex in H, then the operation delta HIN is equal to Hj. So we get another sub-hypergraph Hj, where HIN is the set of vertices in Hi. So in general, we can consider Hi union Hj as Hk, where Hk belongs to this collection of sub-hypergraphs, and any two sub-hypergraphs, intersection of any two sub-hypergraphs is empty. Again, we can consider so many sub-hypergraphs in this collection HF. So together that forms a space, topological space. This can be considered as a dilation-induced space denoted by Ht tau delta HF. This is a morphological dilation-induced topological space defined on hypergraph H. Similarly, if we use the definition of erosion on these sub-hypergraph, we get another topological space that is erosion-induced topological space. So there are so many other operators in mathematical morphology. So we can construct several topological spaces like this. So there are methods to convert data to hypergraph or simplicial complex. So from data, we can construct topological spaces like this. And we have the analogy of continuity in topological space here also. So the analogy is in the form of an adjunction. In the case of a topological space, continuity is defined as a mapping F between two topological spaces, between two open sets, say X and Y. Okay. So here we have to consider two topological spaces, tau h and tau g, and subhypergraphs hi and gj, so that there exists a mapping delta and epsilon. Delta is a mapping from h to g, and epsilon is a mapping from g to h. And delta and epsilon are said to be continuous if and only if delta of hi is equal to gj and epsilon of gj equal to hi, with the condition that epsilon composition delta of hi equal to hi. So this is like an idempotent operation. So if you take the composition of this epsilon composition delta or delta composition epsilon, that operator become idempotent. So here we can visualize this case when we consider two subhypergraphs hi and gj. Okay, take the epsilon delta of hi. So you get subhypergraph here gj, and if you take the erosion epsilon of gj, you get hi. So in that way we can define the continuity and analogy with respect to a topological space. So we can state a theorem like this: if we have two topological spaces induced by delta and epsilon, then there exist open sets hi and hi in hf such that epsilon from gf to hf implies epsilon of gj equal to hi, and delta of mapping from hf to gf defined by delta of hi equal to gj, where delta and epsilon are continuous with respect to adjunction. So using the neighborhood operation, we can define maximal neighborhood using dilation. So when we consider this topological space induced by dilation, h tau delta hf, define the neighborhood operation as n delta v equal to delta of v, where v and delta v belong to hf. Delta v can be called as one-step neighborhood of v. Similarly, we can define two-step and n-step neighborhood. So like this, h is given hypergraph. One-step dilation is denoted by n delta v. This is an one-step dilation of that vertex v, and this is two-step dilation n delta square v, like that. In that way, we can define a maximal neighborhood. Similarly, using erosion, we can define minimal neighborhood also. And minimal neighborhood is defined like this in terms of erosion, using erosion. This is an illustration of the concept. The illustration of this can be shown by taking a sample text and its corresponding hypergraph. Text hypergraph is created by converting words to nodes and sentences to hyperedges. That is applied to a pre-processed text, where the pre-processing task involves several operations like removal, stemming, etc. The application is given in the following figure. Here we are considering the example. We are considering the word score, and consider the two-step dilation, one-step, two-step dilation of this word score. So here score is coming in several sentences. So consider one such sentence. So here score is coming. The number corresponding to this is 20. Okay. Second word is score. So when we consider the corresponding hypergraph, this is a hypergraph corresponding to this text. 20 is coming here. 20 is coming here. So look at the corresponding one-step dilation with respect to word score. This is the one-step dilation with respect to word score, and the corresponding sentence is here highlighted. The first batsman to score a double century in a one-day international ODI. Now consider the two-step dilation. So we get an extended paragraph like this highlighted with respect to the word score. Score is contained in all sentences. You can see that. So in that way, we can define maximal neighborhood. That is the application here. Similarly, we have a definition like maximal open subset. Maximal open subset. With respect to the subsethood, we can define a partial ordering also, because this collection of subhypergraph satisfies this partial ordering relation subsethood. The subsethood relation is given here, and using that we can construct topological spaces using maximal neighborhoods, just as in the case of dilation and erosion induced topological spaces. And these are the these constructions very important in the analysis of data, because this can be applied to segmenting images or documents, and can hence there exist, we can construct more topological spaces and more analysis is possible. This is a theorem regarding this homeomorphism in topology. So in terms of delta and epsilon, we can define homeomorphism as a continuous bijective mapping. And separation axiom also holds here in this topological space, Maximal open neighborhood with respect to PHM. This is the construction of T0 space using K-step dilation and delta KV. Similarly, we have a T1 space. You can see that condition, yes, T1 space, that intersection is non-empty. T2 space, this is T2 space.
Excuse me.
And okay, closure of H1, and this is closure axiom. And we have application in dynamics also. Okay, these are the application of topological dynamics, identification of diseases. Okay, patient disease hypergraph is constructed. Summary of all results.
Please conclude, your time is over.
These are the references. Thank you.
Any questions from the participant side? Okay, thank you, sir, for your presentation.
Thank you.
Please stop sharing the presentation. Next participant is Selvi R. Presentation number CP26.
Hello, ma'am. Can you hear me?
Yes, you are audible. Please share your presentation.
Okay. Sir, we know Ramkumar sir sharing, so I can't.
No, I am not shared anything. I'll check.
Okay, ma'am.
Is it okay?
Yes.
No, sir, I can't share. You cannot start screen share while the other participant is sharing.
I'm not sharing. I'll
Okay, I can now. So I can share. So good morning, everyone. My research topic is fuzzy iterated function system. Let's start with some definitions. First definition is iterated function systems. An iterated function system on a metric space Xt consists in a family of contractions Fk, k equal to 1 to etc. n on capital X, and it is denoted by capital S equal to ordered pair Xd, Fk, k equal to 1 to etc. n. For example, consider the contractions on R defined by F1 of X equal to X by 3 and F2 of X equal to X plus 2 by 3. Then the system closed interval 0, 1, D with these functions F1, F2 is an iterative function system and its attractor is a Kondo set. Next definition is topological iterated function system. It deals with the iteration of a function or a set of functions on a topological Foster space. That is, a topological iterated function system TIFS on a topological T2 space X tau consists in a finite family of continuous functions Fk, k equal to 1 to etc. n, where Fk from X to X is such that it satisfies two conditions. The first condition is for every k element of k star of X. K star of X means the set of all compact subsets of capital X. There exists hk element of k star of X such that k is a subset of hk and union k equal to 1 to n, fk of hk is a subset of hk. The second condition is For every sequence alpha L greater than or equal to 1, with the alpha L belongs to the set 1, 2, etc. n, and every k element of k star of x is such that the union k equal to 1 to n, fk of k is a subset of k, the set intersection L greater than or equal to 1, f alpha 1, composition f alpha 2, composition etc. Composition f alpha L of k has at most 1 point. Next definition is, what is a dynamical system? It is the mathematics of behavior and the classification of how systems change over time. Mathematically, given a function f and an initial value x, what ultimately happens to the sequence of iterates x, f of x, f square x, etc. That is, can we predict what will happen at the last? So next definition is chaos. Let a capital V be a set and f is a function defined on capital V. F is said to be a chaotic function if it satisfies two conditions. The first condition is f is topologically transitive. That means for any pair of open sets u and v of j, there exists a k greater than or equal to 0 such that fk of u intersection v not equal to 0, not equal to not set. That means there exists a dense of it. Second condition is periodic points are dense in capital V. For example, tende map and logistic map. So problem statements. My problems are, suppose f from x to x is a function. We can define fn as a n-time composition of f, and nth iteration of f is defined as f power n for integer value set. So what can be the value of f power r for every r element of r? That is, what will be the rth iteration of a function f for every r element of capital R? And how the dynamics change with respect to this? And how can we check whether a function is chaotic or not with respect to this iterative concept? For solving these problems, I used to define definitions. First definition is r times iteration of f. The r times iteration of a bijective function f, it is denoted by f power r, is a function from capital X to the set of all fuzzy sets of capital X denoted by capital F of x. And that is, f power r is a function from capital X to f of x for every r element of r. It satisfies a condition that supremum of y element of capital X of membership value of y on the set fr of x must be greater than 0 for every x element of capital X. So fr of x is a fuzzy set for every x element of capital X. For example, consider the real space and consider the function f of x defined on R by f of x equal to 2x. Then define the rth iteration of f of x. That means the membership value of y on the set fr of x by 1 by e raised to d of floor f of floor of x, floor of r of x y plus 1 by e raised to d of f power ceiling of r of x y by 2. Then we can find the graph of f power 1 by 100 of 1 by 2 is given here. This is a graph of f power 1 by 100 of 1 by 2. And another example is example 2. Define the membership value of y on the set fr of x by 1 minus f power floor of r of x y minus y the whole square into e raised to minus of f power floor of r of x minus y the whole square plus 1 minus f power ceiling of r of x minus y the whole square into e raised to minus f power ceiling of r of x minus y the whole square whole divided by 2. Then the graph of f power 1 by 100 of 1 by 2 is this. The next example is define the membership value by 1 by e raised to d of f power floor of r of x y into cos modulus of cos 2 pi r. Then the graph is like this. So the next definition is fuzzy iterated function system, which is denoted by FIFS. An FIFS on a metric space capital XT consists a bijective function defined on a metric space capital X and an iterative method FR R element of capital, and it is denoted by capital S equal to X F FR. Next definition is epsilon topological transitivity. For epsilon element of closed interval 0, 1, a bijective function f defined on a metric space capital X said to be epsilon topological transitive in the system X FFR if for every open sets U and V of X, there exists R element of capital R, U element of U, and V element of capital V such that f power R of UV is greater than or equal to epsilon. And the definition for epsilon periodic point is, for epsilon element of closed interval 0, 1, x element of capital X is said to be an epsilon periodic point of a bijective function f on a metric space capital X in the system X F FR if f power R of X must be greater than or equal to epsilon. And using these two definitions, we can define epsilon chaotic function as a function defined on a metric space capital X is defined is said to be epsilon chaotic if it is epsilon topological transitive and the epsilon periodic points are dense in capital X for epsilon element of closed interval 0, 1. For example, let f from S1 to S1 defined by f of theta equal to theta plus pi by 8. And this function is 1 by 2 chaotic in the system S1 f fr. And the next example is consider R with a discrete metric and define f by f as an identity function. Then the membership value function, that means the membership value of y on the set fr of x is defined by 1 by 2 raised to d of f power floor of r of x y plus 1 by 2 power d of f power ceiling of r of x y by 2. Then the identity function f on r is 1 by 2 chaotic. If 2 is changed by e, then this function, the same function will be 1 by e chaotic. If it is changed to a, then for a not equal to 0, then the same function will become 1 by a chaotic. So as n tends to 1, f becomes 1 chaotic. So this is a graph for when a equal to 10, the yellow graph represents f power 1 by 100 of 1 by 2. And blue is for a equal to e, and the red color is for a equal to 2. And the last one is purple color is for a equal to 0.1. So my results are, important results are, if a bijective function is defined on a metric space capital X is topological transitive, then it is epsilon topological transitive for every epsilon element of closed interval 0, 1, but not conversely. The counter example is, consider the function f from S1 to S1 defined by f of theta equal to theta plus pi by 8, and it is 1 by 2 topological transitive, but not topological transitive. The next result is, in the system X, F, FR, F is topological transitive if and only if F is epsilon topological transitive for epsilon equal to 1. The next result, main result is, in the system X, F, FR, F is 1 chaotic if and only if F is chaotic. So these are my results, and these are the references. So thank you so much for hearing my presentation. Hello, ma'am.
Any questions from the participant side? Any questions? Okay, thank you, Sarvi, for your presentation. Now,
Thank you.
since this Zoom, will you please stop sharing your slides? Okay, now this Zoom meeting has got time durations. All of you, please exit from the Zoom meeting and join this meeting immediately now before the next presentation. Thank you.